With real valued functions, once you learn how to calculate derivatives, you learn all sorts of rules for derivatives. Basically, those are rules for how we can take the derivatives of new functions that we can build by combining two functions using arithmetic or composition, or by taking a function and multiplying it by a constant. Now, a lot of those rules are going to generalize to vector functions. The one that doesn't is the quotient rule, because we have nothing that looks like at all like division of vectors. Okay. But theorem 3 basically gives us the vector versions of those rules. So I've got that up here on the board, and it's also in your text. We're going to let u of t and v of t be differentiable vector functions in n space. Could be 2 space, could be 3 space, but they're going to be in the same space. Okay. F of t is a differentiable real valued function, and c is just a real number, just a scalar. Okay. So rule 1, this is just the sum rule for derivatives. The derivative of the sum of two vector functions is the sum of those derivatives. I can take the derivative of each piece and then add them. Rule 2, generalizing the constant multiple rule. If I take a vector function and I multiply it by a scalar, and then I want to take the derivative, well, I can just take the derivative of that vector function and then multiply by that scalar. Okay. Now the product rule, we actually have 3 different generalizations of. Now I don't have a full-on vector multiplication, but I have scalar multiplication, I have the dot product, and I have the cross product. And we have a version of the product rule for all of those. This first rule, rule 3, talks about scaling a vector function by a real valued function. So it would be like f of t is a function that spits out a scalar, u of t is a function that spits out a vector. I'm going to multiply the scalar output by the vector output, and that's what I get here. Well, we get a version of the product rule here. It looks just like the product rule that we know and love. It's just that one of my factors is a vector function. So I get the derivative of f used to scale the vector function u, plus the original function f used to scale the derivative of u. We're going to come back and prove that one in a moment. Your textbook proves, I believe it's number 4, and then you're asked to prove a lot of these in the homework. We're going to be proving these the same way we proved some of the very basic properties of vectors when we first started working with them. We're going to prove things by going to the component level. Back in chapter 12, we took advantage of the fact that the components of a vector were just numbers, so we could use stuff that we knew about numbers. Now we're going to take advantage of the fact that the components of a vector function are just real valued functions, and we know a whole lot about real valued functions. Okay, so we'll come back and prove this one in a moment. Okay. 4 gives me the derivative of the dot product. Now notice, u of t dotted with v of t is actually a real valued function, because the dot product is a number, not a vector. Okay, so this is a real valued function, but it's one that I built out of vectors. And I can build the derivative, which will be a real valued function, out of vectors. It's just a generalization of the product rule, but using the dot product to replace the multiplication. We get something similar with the cross product. I will just mention that with cross products, we want to be careful because remember that order matters when we're taking the cross product. So if I'm taking the derivative of u crossed with v, notice I get the sum of 2 terms. Each is one of the derivatives crossed with the other original function. But you'll notice the u factor is always first. The v factor, whether it's the derivative or the original function, is always second. Okay. So 3, 4, and 5 give us the vector versions of a product rule. And then 6 gives us the vector version of a chain rule. If I were to take my real valued function f of t and compose that with my vector function u, chain rule would tell me I should get u prime evaluated at f of t multiplied by the derivative of the inside part, which would be f prime of t. I've simply written that f prime of t first because, of course, if this is a real valued function, it's spitting out a scalar. And we generally write scalars in front of vectors. So where we're used to sort of writing the derivative of the inside part last, when it's a scalar that's being used to scale a vector function, we would write it first. Okay, So let's see if we can't go ahead and prove property 3. I'm going to prove it in 2 space. The proof in 3 space is very similar. We would just have 3 components. But if we're going to be proving things by going to the component level, we need to know how many components we have. Okay, so I need a vector function that's differentiable, and I need a scalar function that's differentiable. So let's go ahead and introduce them. So remember, let is a great word. It allows us to introduce our options. So let's let u of t be x of t, y of t. So I'm introducing my vector function, and I'm introducing the component functions, be a differentiable function in R2. Now notice, by saying that this one vector function is differentiable, I have just told you that both components are differentiable, because we have a theorem that says we take the derivative component-wise, and so if one of the components isn't differentiable, I can't take the derivative of the whole thing. Okay, I'm going to then let f of t be a differentiable real valued function. And I'm going to just write out what my claim is. So the claim was that the derivative of f of t u of t, that's the vector function I get if I scale the vector function u by the scalar valued function f of t, that this was just f prime of t being used to scale u of t plus f of t being used to scale u prime of t. Notice that claim has a left-hand side and a right-hand side. And when I'm proving something in painstaking, when I'm proving an equation, I can only work with one side at a time. Okay, I'm going to choose one to start with, and I am going to try to prove this in painstaking detail, which means I'm not combining steps, and I'm providing a reason for each and every step. Okay, so let's just take a look. The left-hand side is the derivative of f of t u of t. So I've chosen to start with the left-hand side, and I'm going to try to simplify it. Now, if the key to all of these proofs is to do things at the component level, I want to get to the component level. So we're taking the derivative of f of t, and then u of t was just x of t, y of t. Now, what's my reason there? Remember, this is essentially because I said so. Okay, and the fancier way of saying that is that that's the definition of u. But that means it's very important that when you were introducing your object, you did actually introduce the components of that function u. Okay. Now, this is a vector function being multiplied by a scalar valued function. How do I do scalar multiplication? I scale each component. So I can say this is the derivative of f of t x of t, comma, f of t y of t. It's the derivative of that vector. What did I do there? I did the scalar multiplication, so I just used the definition of scalar multiplication, abbreviating that as SM. Okay. All right, I am out of space, so I'm going to continue at the top of the board here. Now, how do I take that derivative? Component-wise. Okay. So I can say this is the derivative of f of t x of t, comma, the derivative of f of t y of t. Why is that? Because we take derivatives component-wise. That was actually theorem 2, but I don't expect you to remember the theorem numbers. I expect expect you to remember what they say. And what that one says is that we calculate derivatives component-wise. Now this is fabulous because these guys are real valued functions. I get to use all the calculus that I know from 2 semesters of calculus. I got this one in first semester calculus. I get to use the product rule. Now notice, we are proving a version of product rule for vector functions. I'm going to use the product rule for real valued functions. I can do that because I know stuff about real valued functions. So just like in our previous proofs, the reason vector functions are going to have certain nice properties is because their components are real valued functions. And we know stuff that's true about real valued functions, and anything we're doing at the component level then is going to inherit those nice properties of real valued functions. So now I can say that first component is just f prime of t times x of t plus f of t times x prime of t. And that second component is f prime of t times y of t plus f of t times y prime of t. And what's my reason there? Product rule. But if I stop there, I haven't said enough, because I'm trying to prove product rule. I'm basically not allowed to use product rule to prove product rule. But I am allowed to use the product rule for real valued functions to prove the product rule for vector valued functions. And that's exactly what's happening here. Okay, so if I look at this, now each of my components has 2 terms in it. And I know I'm ultimately trying to get to a sum of 2 vectors. So I'm thinking I want to split this up into a sum of 2 vectors. If I take a look, this component, this first term and this first term, both have an f prime in them. And the second terms both have an f in them. So I think I'm going to split this up into a sum of 2 vectors. For the first vector, I'm going to take the terms that have the f prime in them. Okay. So that would be f prime of t times x of t, comma, f prime of t times y of t. That's what I've got underlined once. Plus, in the second vector, I'm just going to put the second terms. F of t, x prime of t, f of t, y prime of t. Okay. Now, what I just used there is the definition of vector addition. Sometimes a little bit easier to see that when you're taking 2 pieces and combining them. I would just add these 2 to get this term, and then add the second components to get this. But equality works in both ways. If this is the same as this one vector is the same as the sum of these 2 vectors, and that is the definition of vector addition. Now, I'm choosing to just sort of keep going. I'm hoping to ultimately arrive at the right-hand side of things. If you preferred, you could have gotten to this point and said, okay, I've simplified the left-hand side. Now I'm going to start a new equation and simplify the right-hand side until I get to the same thing. Okay. All right. Now, if I look here, both of these terms had an f prime in them. And that's just a real valued function. So that's spitting out a scalar. For all values of t, f prime of t is just a scalar. So I can say that's f prime of t scaling the vector function x of t, y of t, plus here, both of these components have an f of t. And again, that's just a real number, so that's just a scalar. So this is f of t, x prime of t, y prime of t, and we're almost there. This vector has a name. Oh, sorry, I need to give my reason. Oh, almost forgot, painstaking detail. That's the definition of scalar multiplication. All right, now this vector has a name, so that's f prime of t times u of t, plus, what's this vector? That's actually just u prime, because we take the derivatives component-wise. Okay. So I can say this is f of t times u prime of t. So here, this is, I'm not going to count this as doing two things. I basically replaced this with what the vector that it was, and this with the vector that it was, but I have slightly different reasons for those. I'm going to count that as we're still doing one thing at a time. Okay, so this would be, I'm running out of space here, so my reason there would be the definition of u, because we explicitly stated that at the beginning, and the fact that we take derivatives component-wise. So that makes this the derivative of u. Okay. But if I take a look at this, that's exactly the right-hand side. Oh my goodness, I've completely run out of space. That's exactly the right-hand side of my claim. So I would want to just acknowledge that's the right-hand side, and so thus the claim is true. Or if you prefer, you could write QED, which is a fancy way of saying thus the claim is true. Excellent. So you will be doing some proofs in the homework. I do expect you to do those at the component level in painstaking detail. And so I do have, anytime there's a proof assigned, there are solutions that are posted on Canvas. But doing a proof is kind of like writing an essay, and yours probably isn't going to match mine exactly. So if you have questions, if you look at mine, you look at yours, and they're not exactly the same, it doesn't necessarily mean yours is wrong. If you have questions and want some feedback on your proofs, feel free to let me know. Just email them to me, bring them to office hours, whatever, but I'm more than happy to give you feedback on those.